Very simple things happen when the electron encounters you. This electron is, of course, present. Our surroundings are filled with atoms. If there are atoms, then there are electrons. So it starts to do something called interacting with the electron, and then it begins to emit particles, as you can see. Look at what is happening. The electron is going, the electron sees two gamma photons, one moving in this direction and one moving in the opposite direction. Here, the patient has started to enter the bedside. This bedside has a specific design that we will discuss later. It begins to detect the two gamma photons using a specific crystal and starts to give you a whole body image, as you can see. This is the general idea of radioisotope imaging. Is this clear so far, doctors, or is there a problem? All right, great. Now let's delve into some important details. We have a general idea and understanding of where we are going with the patient, the radioactive substance, and the injection. The discussion is now clear. We have grasped the fundamentals of nuclear imaging. As I mentioned, the substance will enter the spectrum device, and this is the spectrum we talked about earlier. Here it is, the one that is present. This is the lateral wall view, and this is, of course, the view of the left ventricle, and this is the view of the right ventricle. There is a defect in the inferior wall. This defect indicates that it is ischemic. So, you are observing function or physiology in the nuclear image. Now let's talk about, we mentioned in the X-ray section that I deal with the difference between the physical properties of the objects, specifically the atomic number of the materials. Bone absorbs more than soft tissue, and bone absorbs more than fat. So you are working on the difference in the physical properties of the materials, and thus the image that comes out depends on this difference. What are you working on? You are working on the X-ray photon. We said that X-rays can be considered monoenergetic or polyenergetic. They are polyenergetic. In radioisotope imaging, you work with kilovolts and milliamperes to control the energy output, or the spectrum that comes out, or the number of photons that come out. In radioisotope imaging, you introduce a radioactive substance, and this radioactive substance has its own specific properties. For example, you might hear someone say, I use technetium. The patient might undergo treatment or diagnosis for the thyroid gland or treatment, so they use iodine, which is another radioactive substance with different properties. The gamma photons emitted from it have different energy compared to the energy of technetium. Each radioisotope has its own signature. The technetium's fingerprint produces 140 kilo electron volts, which is the energy of the gamma photon at 140 kilo electron volts. On the other hand, iodine produces 324 kilo electron volts. Each element has its own energy signature. When you inject the patient with the radioactive substance, you cannot simply say that you will increase the milliampere. All you can do is adjust something called the dose, which is the amount of administered activity that will affect the patient. This has an impact on image quality, scan time, and patient dose. For example, if I give a high dose of the administered activity, the patient dose will also be high. Now, if I give a higher dose of my radioactive substance, will that produce a better or worse image? As we will see later, factors affecting image quality in nuclear imaging differ from those in X-ray imaging, where key factors included milliampere, rotation, and exposure. Here, I am working with some acquisition parameters. In radioisotope imaging, it affects the image quality, and there are factors related to the radiopharmaceutical that I inject, which impact the patient. Let's start from the beginning. We all know very well that the atom has a nucleus, and around the nucleus, there are orbitals where electrons move. Is there any disagreement about this? There is no disagreement. Inside the nucleus, what is there? There are protons and neutrons. I know this is a bit of boring physics, but it's important. We all hear that the neutron is neutral, meaning it has a charge of 0. The proton has a positive charge, and the electron has a negative charge. The electron is outside the nucleus. The nucleus contains protons and neutrons. So, what makes me say that I have a stable atom or a stable nucleus, or that it is not radioactive? And I say that I have another atom that is unstable or radioactive, which emits radiation. We talked about this at the beginning of the lectures in the first part of the course. Does anyone remember the number of neutrons? Right, the number of neutrons is important for the balance between the numbers of neutrons and protons. If I have an excess of neutrons, my atom or nucleus becomes radioactive. If my number of neutrons has a slight defect, it means that the protons are higher, and my atom also becomes radioactive. I may have mentioned before that I understand that protons have a positive charge. So when their number is large inside the nucleus becomes uncomfortable because there is repulsion among the protons due to their large number, and it needs to stabilize. So the nucleus stabilizes. This is logical. But what if the neutrons are the excess? But Dr. Islam, you just said that neutrons have no charge. What makes the nucleus radioactive when it has a high number of neutrons? There is a theory that talks about this subject, which tells you that inside the proton and inside the neutron, there are charged particles. The proton contains 3 particles. 2 are called up quarks, and 1 is called a down quark. The neutron has 2 down quarks and 1 up quark. We won't get too caught up in this, but I want you to understand what gives the proton a +1 charge, and what gives the neutron a 0 charge. The up quark is what gives the proton, which has 2 up quarks and 1 down quark, its charge. The down quark has a charge of 1. The up quark has a positive charge, and its charge magnitude is related to something called spinning properties. We won't delve into that, but I want you to know that the sum of the charges inside the particles within the proton is +1, and the sum of the charges inside the neutron is 0. From this equation, we see that there is 1 up quark, which gives a charge of +2. So that makes it 0, meaning this is your charge of 0. Now, it was mentioned that there are quarks, and these quarks have charges, as we were discussing. It was said that if I have the number of neutrons increased, and this increase caused the internal quarks within the neutrons to interact with each other, resulting in repulsion between them. This is why it is said that there is an unbalance in the number of neutrons to the number of protons. This imbalance occurs because the neutrons and protons inside the nucleus are arranged in a specific way. And this arrangement is what causes the stability of the nucleus. If there is a disruption in this arrangement between the neutrons and protons, the atom can become radioactive or unstable. If I say right now, here is the line that has both neutrons and protons equal to each other. Here is the number of protons on the x-axis, and here is the number of neutrons on the y-axis. And this is the line of stability. What does that mean? It means that the ratio between protons and neutrons on this line, at the values present on this line, indicates that your atoms are still stable. This is the ideal situation where protons and neutrons are equal. Now, if there happens to be an excess number of neutrons or an excess number of protons, what will happen? You will find that several things occur. This is a relationship between the adad and neutronat on X and the added brotonate. It tells you that in zone A, zone B, and zone C is for materials that have an al-adad al-dhari above 83. Elements above 83 are considered unstable. Okay, zone A is also unstable and zone B is unstable. So what does F zone A mean? It refers to atoms or materials or radioactive materials that have a low add neutronat and a high add brotonat. So here in zone A, we have a high add brotonat and a low add neutronat. As for zone B, it's the opposite. It has a high add neutronat and a low add brotonat. Now, zone C consists of heavy particles or heavy atoms. Heavy atoms mean that their add zur or add brotonat is greater than 83. If we also remember that I mentioned I have something called, for any given element, the ZD number, which is also known as the atomic number, and the L mass number, which is referred to as the mass number, are specifically defined, where the ZD number is the total number of brotonat, which are protons, or the number of electrons. The L mass number, on the other hand, is the sum total of brotonat, which are protons, plus added a neutronat, which are neutrons. So, the al-adad al-dhari, which is the atomic number, is responsible for determining the chemical properties of the atom of the substance, meaning it determines the chemical reaction. For example, if you have an element like iron or copper or any other element, the one that determines its reactivity and chemical interactions is indeed the atomic number. On the other hand, the L mass number, which is the mass number, determines its physical properties. Now, if I have two elements that have the same al-adad al-dhari, which is the atomic number, but different al-mass number, which is the mass number, I call them what? I call them an-nadha'ir, which are known as isotopes. Isotopes are materials or atoms that have the same al-adad al-dhari, but different al-adad al-kutali. This means they have exactly the same adad al-brotonat. For example, carbon has an atomic number of 6, which is its al-adad al-dhari, and it can have mass numbers such as 12, 13, and even sometimes up to 14. These represent its various al-adad al-katali values. All of these isotopes possess precisely identical atomic numbers, but differ significantly in their mass numbers. Hence, we refer to them collectively as an-nadha'ir. Some specific types among these an-nadha'ir are known specifically as al-isotope al-musha, due to their radioactive nature. The reason they exhibit radioactivity lies in a distinct imbalance between added al-brotonat and added al-neutronat within them. When you increase this mass number further still, it causes a noticeable difference regarding proton counts present therein. For instance, carbon-12 versus carbon-13, alongside also including cases like carbon-14, all differing primarily based on varying levels concerning ta'dad al-neutronat involved herewithal. If there exists any pronounced imbalance between both ta'dad and neutronat, along with corresponding ta'dadat proteiniya, then indeed said isotope becomes classified under what's termed, technically speaking, radioisotope. Save them! The isotope became known as the radioisotope. So, I have a type of isotope that I call regioisotope. If I say that the atomic number is responsible for the chemical and metabolic properties of the elements, it means that if I have two elements, like carbon-12 and carbon-13, both of them have the same atomic number and are present in a bottle or a test tube. Can you separate them? I can't. Why? Because they have the same chemical properties. That's why a patient, for example, who I will treat with iodine to address their thyroid gland and provide treatment for thyroid cancer, will be given iodine, specifically iodine 131. During the treatment period, the patient should not eat anything containing iodine, such as iodized salt, because it contains sodium iodide. Why? Because regular iodine and the radioactive iodine, which is iodine 131, are considered isotopes of each other. If you give regular iodine, the thyroid will not be able to distinguish, leading to competition between radioactive iodine 131 and regular iodine. This means that iodine 131 will not enter the thyroid in the desired amount and the treatment will not proceed correctly. Therefore, we tell the patient not to eat fish or anything containing iodine. This is why the patient undergoing the PET scan is administered FDG. It tells you that your sugar level needs to be at a certain level, right? Why? Because it prevents him from eating anything with sugars before the scan. Why? Because the same idea will create competition between him and the glucose present. And consequently, what will happen? It will reduce the accumulation of radioisotope tumors that exist. So when you do imaging, you won't see the image correctly. If the isotopes here have two atoms or two elements with the same atomic number, the problem is that I can't separate them from each other, right? But if they are different, you can separate any two materials with different atomic numbers, and they will react in different ways, like different chemicals, allowing you to separate them. The mass number is the protons plus neutrons, which is responsible for the density and the physical properties of the atoms or the neutrons. In case you have an excess number of neutrons, what will happen? The atom wants to stabilize. So what will the doctors do? They will convert neutrons into protons when there are too many neutrons. What should I do? I can make a neutron inside the nucleus turn into a proton, and as a result of this transformation, something called beta minus is emitted, which is the beta particle. So, what does this happen in? It happens in iodine 131. Iodine 131 emits beta particles. And by the way, it also emits gamma. So they always tell you that the gamma photon follows beta emission after beta, plus or beta minus, as we will discuss shortly. Gamma radiation is also emitted afterward. It doesn't just show beta emitter, but it is a beta emitter and also emits gamma along with it. The gamma is emitted from the nucleus. Okay, the range of beta minus is the distance it can travel inside the patient's body, measured in millimeters. Millimeters, what does that mean? Beta particles are considered a type of energy, a form of radiation. I have beta, I have beta minus, I have beta plus, I have gamma, I have alpha. These are the main categories. There are also neutrons, but that's not our topic right now. In beta minus decay, when there is an excess number of neutrons, one neutron transforms into a proton, resulting in beta minus decay. So what happens to the atomic number? Your atomic number increases by 1. It increases by 1 because if I have, for example, material X, this material, for instance, let's come here. Iodine 131, right? So what is the atomic number of iodine? It's 53. So what does this atomic number represent? It represents the number of protons. Now, why did it transform into xenon, which is a different element? Why is it a different element? Because, as I mentioned, there was a change in the atomic number. If the atomic number changes, then you are talking about a completely different element. Now, the mass number of xenon was 131, the same as that of iodine, but its atomic number was 54, so the atomic number increased by 1. I also want to understand why, when a neutron transforms into a proton, the atomic number increases by 1, while the mass number remains the same. This is simply because when you convert a neutron into a proton, the mass number stays the same, because the loss of neutrons is compensated by the increase in the number of protons. The mass number is essentially the sum of the number of protons and neutrons, so you decrease the neutrons but increase the protons, so it remains unchanged. However, in the case of the atomic number, the neutron is converted into a proton, so the proton increases, which means the atomic number must increase as well. There is nothing that will decrease the atomic number. You have increased the number of protons, so your atomic number has increased. In beta minus, a neutron is converted into a proton, and the atomic number increases by 1, while the mass number does not change. There is no change in the mass number. Beta minus. Or iodine 131 is used in treatment because it emits beta minus particles. These beta minus particles are considered particles that lose all their energy over a short range, meaning they travel a short distance. When I administer iodine 131, it goes to the thyroid, and the thyroid begins to interact with the beta particles deposited in it. Do you remember the topic of radiobiology I was talking about? The beta minus interacts with DNA, leading to the stimulation of cell apoptosis, resulting in cell death. Thus, tumor cells die due to the ionization caused by beta minus. This is regarding the neutron to proton conversion. In beta minus decay, if you have an excess number of neutrons compared to protons, a neutron transforms into a proton, resulting in beta radiation. On the other hand, if I have a larger number of protons and a deficit in neutrons, what happens is that a proton turns into a neutron, giving me beta plus. Beta plus is similar to fluorine, which is found in glucose. For example, in the case of A18, the mass number is 18 and the atomic number is 9, which transforms into oxygen, meaning it becomes a different element with a mass number of 18 and an atomic number that has decreased by 1. There is no change in the mass number. So, the same idea applies. A proton turns into a neutron, and the increase in neutrons compensates for the decrease in protons, so the mass number remains the same. So, the proton affects what? It also affects the atomic number. If I reduce the proton, the atomic number will decrease by 1, so the atomic number becomes atomic number minus 1. All right? In beta plus decay, there is a reduction in the atomic number by 1 without changing the mass number, and it emits a beta plus particle. Now, what does the beta plus do? The beta plus particle interacts or undergoes an annihilation process with any electron nearby, giving me 2 gamma photons at 180 degrees, and the proton number will produce a positron. Einstein said that when there are many protons, a proton transforms into a neutron, giving us oxygen. Then the positron is emitted, which can attach to any electron present in the medium. If you look about 2 millimeters away, 2 gamma photons are emitted, each at an angle of 180 degrees. The energy of each emitted photon is 511 kiloelectron volts. The energy of the photon moving in this direction and the energy of the photon moving in that direction, each of them has an energy of 511 kiloelectron volts. Where did this value come from? It comes from Einstein's equation, which states that energy is equal to mass times the speed of light squared. Here m is the mass, which refers to the mass of the positron and the electron. When we substitute the mass of the positron and the mass of the electron into this equation, the energy comes out to be 511 kiloelectron volts. All right. When I had an excess in the number of protons, it was mentioned that there is a decay method or another method that occurs besides beta plus decay. Keep in mind that we are talking about the ways atoms want to get rid of instability and become more stable. We talked about beta minus decay, which involves an excess number of neutrons and protons. It was mentioned that there is another process called electron capture, where you have a nucleus with a high number of protons. The positive charge inside the nucleus, when it becomes very high, especially with heavy atoms mean a high atomic number, creates an attractive force on the electron present in the shell, pulling it in. When it pulls in the electron, it transforms into a neutron. This neutron, if it stabilizes the nucleus, is what electron capture is about. If we imagine this electron capture, let's think about it.